Question 7 from Paper 2 of the 2024 Higher Physics Examination from the SQA. The art of matryoshka involves making a set of wooden dolls of decreasing size that are placed one inside another. When one doll is opened up, a smaller one can be found inside until eventually the last one, the smallest doll, is reached, and the smallest doll is usually a solid piece of wood. A student states particle physics is just like the matryoshka dolls. Look inside a particle and you'll always find something similar, just smaller. And for 3 marks you've got to bring up some of your knowledge of physics to comment on that statement. Well, as an all-open question, try to get as much physics in as you can. Here's a few suggestions of what you can do, and we'll pull out some tabs here to reveal what is basically some ideas. The matryoshka dolls are like the hunt for particle physicists, you might say, because to find the fundamental particles, that is, particles are not made of other particles. The last doll in the set would be a fundamental doll. You're making a physics statement, you're saying that a fundamental particle is the one which can't be broken down. So that's you showing off that bit of physics. So these dolls are like the hunt by particle physicists to find the fundamental particles. That's particles that are not made of other particles. So the last doll in the set, the solid one, would be the fundamental doll. Just what particle physicists are trying to do with matter. And curiosity leads us to keep lifting each doll's head to see what's next, and really that's what particle physicists are doing. They're just peeling back, not dolls' heads, but they're peeling back matter to find out what's behind it all and what's the most fundamental particle that makes up all matter. In particle physics, the particles that make up, say, a proton are not similar, as mentioned in the statement there. They may be smaller, but they have different characteristics. The 3 quarks that make up a proton are not identical to proton. Yes, they are smaller, but they're not identical to proton. And once again, you're using some of your physics there to answer this question or to debate it. And we can see that situation there because there's the 3 quarks making up a proton, up and up and down, and they're definitely not like a proton, definitely not. And also there's no mention of the forces there in these as doll. In fact, if you open up the head of the doll, you very rarely get 3 of these dolls together like that. So that's another sort of kind of negative comment about this kind of model. You don't get, you maybe get smaller dolls, but in fact they're all the same. But in particle physics you get smaller particles, but they're not the same as the bigger particle. Okay, and this one here, it says to see what's inside a matryoshka doll, you merely lift it, just lift the head off it. To see what's inside a proton, you have to collide them together using a particle accelerator, a large hadron collider. And a hadron is a particle consisting of quarks and held together by the strong nuclear force. So that's the sort of kind of things you have to put down for a statement. Ultimately, you're looking for the fundamental particle. In the case of the dolls, the fundamental particle is just a smaller version of the big doll, only it's a more solid. In real-world particle physics, the fundamental particles that we know of now, the quarks and the leptons, they're not identical to the atom or to the proton or to the neutron. They are a different species altogether from the thing that they make up. So I hope that kind of helps you. Plenty to go on there. And it's always a wee tip now, as we're living in the world of AI, to run that question through AI and see what AI says about it. Question 8 from Paper 2 of the 2024 Higher Physics Examination from the SQA. There's a lot of reading in this question. A group of students is conducting an experiment to investigate the relationship between the power output of 2 small filament lamps and the relative brightness of each lamp. The relative brightness can be determined using an oil spot photometer. Now, we've never come across that before, but we'll read on and see what it's about. The experiment is set up as shown, and you can see we've got lamp 1, we've got the observer. Lamp 1 is a distance d1 away, and lamp 2 is a distance of d2 metres away from the oil spot. And both lamps are separated by 1 metre. The oil spot photometer is a piece of card with an oil spot on it, which is used to compare the brightness of 2 light sources on either side of the photometer. When the relative brightness of the light on either side of the photometer is equal, no spot is observed. And we read on in this question, more reading. The students keep the brightness of lamp 1 constant. The brightness of L2 of lamp 2 is measured using a light meter. The photometer is moved until no spot is observed, and the distance D2 between lamp 2 and the photometer is measured. The brightness of lamp 2 is then increased, and the process is repeated, and the following results are obtained. Then you get that table of L1 and D2 measured in the appropriate units. Now, for 3 marks, we're asked to use all the data. The examiner is telling you with bold letters here, all the data, so we've got to use every line of that table. To establish that the relationship between the brightness L2 and the distance D2 when no oil spot is observed is L2 divided by D2 squared equals a constant. Well, you make up the table, take your time. You have L2 and you just copy the column down, D2, copy the column down, and then with your calculator you do L2 divided by D2 squared and you record your answer. 10 divided by 0.495 squared, you record your answer. 15 divided by 0.606 squared, you record your answer until you get to the final line in that table. And you can see from that final column there that we have L2, and if it's divided by the distance D2 squared, it's always going to equal to 40.8. So we can say then that L2 divided by D2 squared is going to equal to a constant number. And that's us used all the data to show for our 3 marks. Part B of question 8, it says suggest why small spherical lamps are used for the experimental procedure. Well, in this case we have to be as close as possible to a small point source which radiates light in all the directions. If you used a large filament lamp, then the filament is spread out and the light is not radiating out in a kind of radial pattern if it's made like that. So the best idea is to get a small, but it's got to be near a point source as possible, and it's got to be a point source of light, and it must radiate in all directions. So the only way to overcome that is to use a small spherical lamp. That's going to give you as near as it can be to a point source, and the light is going to be radial from it, which means it's going to be spread now equally in all directions. That's for 1 mark. Question 8 continued, part C. The students repeat the experiment outside to determine the luminosity of the sun. Luminosity is a measure of the radiated electromagnetic power measured in watts. The setup for this experiment is shown below. You can see the diagram. We've got the observer looking at the oil spot, we've got the sun's rays, and we've got the filament lamp. The luminosity of the sun can be determined using the relationship which we found out in the previous part of the question. Luminosity divided by D squared is going to equal to a constant. In this case we've got the luminosity of the lamp divided by small d squared is going to go to the luminosity of the sun divided by capital D squared. And we're showing all the particular variables there. The luminosity of the lamp is 1.0 times 10 to the power 2 watts. The approximate distance between the sun and the earth is shown to be 1.5 times 10 to the power 11. And the students adjust the photometer position until the oil spot disappears, and notes the distance between the centre of the lamp and the photometer. And of course the student repeats the process 5 times and records the following results. And as the results here we have got 0.88 and 0.86, 0.90, 0.89 and 0.86. And for 1 mark we're asked to find the mean distance D. So the mean distance D is going to equal to the sum of the readings. So we just need to add up all the readings in our calculator, sum of all the readings, and divide by the number of readings it's going to be there. So the sum of all the readings comes out to be 4.39, and that's going to be meters. And we divide by how many is there? 5, and we therefore get the mean distance. It comes out to be 0.88 meters. Now the next part of the question, it says down here, it says calculate the random uncertainty in the mean value for D. Well, the random uncertainty is found by taking the maximum reading. This is the random uncertainty, we'll call it that. It's equal to the maximum reading, take away the minimum reading, and divide by how many we have as a set of readings, 5 in this case. So the maximum one there we can see is going to be 0.9, so bracket 0.90. Take away the smallest reading, which is going to be 0.86, and we have to divide that by 5. So when we do that, we get an answer of 0.008, and therefore we have to round that to 0.01 to give us the same number of decimal places there. So the random uncertainty is going to be 0.01 of a metre. Question 8c, part 3. Using the data from this experiment, determine the luminosity of the sun. And we don't need to put down the uncertainty value which we calculated in the last example. Okay, so we know what the equation is. We've just been through that. It's the L lamp over D squared equals L sun over capital D squared. And we know the values to put into that equation. There it is there. The lamp 1.0 times 10 to the power 2 watts. After the luminosity of the sun, we know small d and we know capital D. So all we have to do is plug that into the equation. So we know if we cross multiply this equation here, we get L lamp times D squared is going to equal to L sun times D squared up here. So we get that equation there, and what we can do from that, we can rearrange to find what the luminosity of the sun is. So there it is there, the luminosity of the sun is going to be the luminosity of the lamp times capital D squared divided by D squared. So all we have to do is put in our values for that. So we can put in our value as follows. And there it is there, we have the luminosity of the sun is 1 times 10 to the power 2 times 1.5 times 10 to the power 11 squared divided by D squared is 0.88 squared. And we end up with the luminosity of the sun to be 2.91 times 10 to the power 24 watts.